Let's get started. Hope you are all doing well. I hope you enjoyed Matre's lesson on multilingual language models. And today we are actually coming to the last lecture of the language modeling part. There is way more I would like to say, but we need to wrap it and cap it somewhere. So what we are going to finish on is talking about how some of these large language models are capable of taking inputs that are not just textual. For example, you might have used GPT-4 or ChatGPT by providing an image or maybe even directly speaking to it. And just as a maybe motivation of what kind of things models that process both images and text can do, I will share with you this very short 2-minute promotional video.
Is this option vegan?
No, this option is not vegan.
Count the number of people.
Counting the number of people shows a total of 21.
Convert this table to JSON.
Here's the table converted to JSON format.
I want to sell my bike on Craigslist. Write me a description for it.
Schwinn bike for sale. Blue with white accents. $300 or best offer.
You want to buy it?
It's Monday at 1 p.m. Can I park here and for how long?
Yes, you can park here on Monday at 1 p.m. You have 6 hours left to park.
I really like electronic music. What show should I go to?
If you're into electronic music, you should definitely check out the show featuring Tycho and Zed at the Showbox Soto.
Can you write me a knock-knock joke?
Knock knock is there. Rocket. Rocket who? Rocket to the moon and back, baby.
Can you point to the model that takes the least time to train?
Nice. That is really good. Which of these models uses reinforcement learning?
The image shows a table of different models.
Oh, nice.
and
It
their
pointed at the
associated
models.
methods.
Hey, Mama, order me a pumpkin spice latte from Starbucks.
I'll place the order through Uber Eats. Your pumpkin spice latte is on its way.
All right, so what we have seen here is a various examples of instructing a model by providing an image and asking it to do something, and then the model is able to process both the image, the utterance, and perform some of the actions. Okay, let me just do one thing. Sorry about that. This is gonna be done fast. Okay, Fatima, you are now a co-host.
Right, thanks.
And okay, everyone will be muted upon entry. All right, sorry about that. So yeah, what we have seen is these various examples of vision and language tasks. So today what we are, oops, sorry, I'm trying to move to the next slide. So what we are first going to do in today's lecture is go into the details, technical details of how can a model process both image and text and generate a sequence of words. So that's going to be our first goal. And then hopefully we will also have time to talk about how do we prepare, process videos and speech. So let's get started. First, we are going to talk about how to process images on their own without text. And remember way back when I was teaching transformers for the first time, way back before the fall break, I told you that we had all these different neural architectures specialized for various domains like computer vision, natural language processing, speech, translation, reinforcement learning. And then everything turned to into something that can be processed by a transformer architecture. So that also happened in computer vision. So our images are going to be processed by a transformer. This is a little visualization of how that's going to work. First, we are going to start with an image, and then we are going to dissect this image into patches, meaning we are going to define some patch size. Let's say we are going to start with certain image resolution, and we are going to say, let's take patches that are 14 pixels by 14 pixels, and then we are going to move that window shape across our image and take all the patches of this image that fit that size exactly, such as here we have 9 patches, and I don't know what the image resolution is in the beginning, but we had certain size of a patch, and by dissecting it with these patches, we ended up with a sequence of 9 image, parts, which I call a patch. And now, knowing what you know about transformers, in your head, you should immediately think about, okay, we need to produce a sequence of embeddings, because that's what we have been working with when we were talking about transformer designed for text, right? Where we had tokens, each token was represented by an embedding, and then we provided this sequence of embeddings to a transformer. It did self-attention and feed-forward layers for us, and so on. And we will do mostly the same thing here. These patches are right now 2D matrices in a way. We can think about each one of them being a 2D array of pixels. And it depends how do we represent pixels, whether this is going to be turned into a 3D tensor or not. For example, if we are working with a grayscale, then all we need to record is the intensity of the black color. So for each patch, which is in a grayscale color scheme, we would have a 2D matrix where on each value in that matrix would be the color of that pixel at that position of the image patch. However, our transformer, the way we know it, doesn't take 2D tensors as inputs. Rather, it takes 1D, one-dimensional vectors as inputs. So what we need to do is turn our matrices, each one of these matrices into a vector, right? And we can do that by doing our standard linear projection. Namely, we introduce a weight matrix and we downsize this 2D representation into a vector. Excuse me, that's not correct what I just said. We will need to do something differently. So forget what I just said. We are not going to directly apply the linear projection, rather. And okay, now that you know what linear projection is, can someone tell me why linear projection of a matrix wouldn't give me a vector? How did we operationalize linear projection before? And why wouldn't that then work here? Can someone explain that to me? Okay, you all have practiced the writing of the linear transformation in your exams. So let's say I have a vector and I want to linearly transform it to another vector. What would I do?
You put it through a linear, like linearization algorithm.
Not really. So it's pretty simple. I don't know what linearization algorithm are you referring to here. I'm asking for one simple mathematical operation between matrices and vectors.
Do we unfold it into so do we unfold the matrix into a vector like 5 by 5 into 25 by 1 pixel vector?
That's not answering my question. My question is, forget what you're seeing here. Let's go all the way back to not confuse you. You have a vector. What do we do when I say linearly transform this vector? What kind of operation?
It is going to be matrix multiplication.
Yes, right. So we introduced a weight matrix, which is basically encoding the information about the new vector space where we want to transform a vector into. So when we have a vector and we want to linearly transform it into another vector, we multiply the original vector with the new weight matrix. So the answer, very concise answer to this question would be that matrix vector multiplication. This is how we define linear transformation of vectors. Now, why did I make a mistake? I had a 2D array or a matrix. So if I did a linear transformation, namely multiply it with another matrix, I would get the matrix as the output, not a vector, which is not then solution to the thing I said we should set out to do, which is to produce a single vector out of this image patch. So someone else had sorry, I didn't catch your name while you were speaking, but someone had mentioned that before we apply linear transformation, we need to transform this matrix into a vector by flattening it out. And we are going to do that. Let me go. Maybe I'll come to that here. I'm just going to give you a high-level overview. We are going to flatten by these matrices by basically taking the rows in each one of these image patches and concatenating it into a vector. In this way, we are going to flatten each one of these image patches, and then we are going to linearly transform it, that flattened vector into a new vector to downsize it into something which is reasonable embedding size, because here, depending of what the resolution of our image is, we might end up with enormous flattened vector out of this image patch. Ganesh, I think you have a question?
Yeah, so do we also add positional encodings to this? So I see like
That's
so
right.
There is towards row and towards column, there is some sort of information that's carrying around. So how do we like if we do positional encoding, like what's the process there?
Yeah, so we are going to go into details of all of this. I'm just going to give you a heads up answer that as we had with language models, we are going to have positional embeddings, namely a special embeddings from position 0, 1, 2, 3, 4, all the way to the maximum possible position. And these are going to be learned embeddings that we are going to just sum with each one of these embeddings stemming from this process where we went from image patch to flattened vector to linear transformation of that vector. So see here you have a red vector and a purple vector. Those are going to be summed together to produce a final embedding of a given patch that's going to be processed by a vision transformer. Again, I'm going to go through this step by step. So if you are feeling like I'm going too fast or it's too high level, don't worry, because we are going to go into steps a little bit slower and in more detail. But what point I'm going to try to make here is that once we had the original image and then we produce this sequence of patches and transform each patch into an embedding, then your computations that come after from your transformers are exactly the same as you have seen it with language models that you worked with just text, right? Because now we just have this sequence of embeddings like we had before. So we made this, abstraction. We made this new representation of our image that's exactly the same as what we had before, and therefore we don't need to change any of the subsequent operations. Okay, let's go into this a little bit more carefully, though. I wanna before I go into like step-by-step equations, I wanna show you a visualization of 32 by 32 image that is then dissected into a sequence of 64 patches of size 4x4. So given some image, we ended up with this sequence. Does anyone have immediate reaction to this? How does this look to you? Does it look reasonable? Is this how you imagined we are going to process the images? Nate, you are nodding. Can I ask you to tell more? No worries.
I'm in the library, so it might be a little loud. It makes sense how it's processed just from the top and then it goes through the side. So it doesn't look exactly like the image because the vertical component of it isn't there, but I think the horizontal component is. So it looks weird, but it makes sense the way it's processed, if that makes sense.
Yeah, well, I will kind of pinpoint to what you said. It looks weird because that's my immediate reaction when I see this, right? Like the way we have our visual perception as humans is to not do something like this, right? Like you're not linearizing these patches, and then, as you said, we lost this vertical information. So now I couldn't find what was the original image for this sequence of patches. And I don't know exactly what this image represents, right? Like reconstructing the original image is pretty hard, right? So my immediate reaction is that this looks pretty weird, and it's kind of strange that this is, this is what we are using to actually very successfully process images. So when we go way back, when I introduced sequence-to-sequence models, I said where there is this whole line of work where inputs themselves are not inherently sequences of anything, but to able to use transformers, we still turn them into sequences of something. And for me, that's a little bit disappointing sometimes, especially when we have more intricate structures such as graphs or tables. Okay, so that's how these sequences of patches look like. So now I'm going to go step by step. How do we produce these sequences of embeddings starting from an image? If you have any clarification questions, please jump in. I would love that this is clear to all of you. So what we start with is an image that I'm denoting with X. X is is a tensor, 3D tensor. I'm going to go over how we denote shapes a little bit more carefully, because I did notice that that's maybe not something you are all super accustomed to, despite me assuming you are. So when we use X between these letters, that means that these are separate dimensions. If I have used just a normal dot, that would not be meaning that there is a separate dimension. So from this right up here, we know that this is a 3D tensor. The first dimension denoted with H refers to the number of rows of pixels in the image. So each image is just a 2D array of pixels, right? So Age denotes how many rows there are, and you can think about this as the height of the image. And then W refers to the number of columns of pixels in the image, which refers to the width, which is a common way how we denote the resolution of images. H by W is standard way of writing the resolution of images. And then we have this third dimension referred to as C, which refers to the channels. And this is how we want to represent the color of our image. If you have grayscale, then C equals to 1, because you only need to work with black color and change how intense it is. However, if you do want to have color, the standard format is RGB, standing for red, green, and blue color. And here, then each pixel is represented by 3 values. And when you combine those values, you get the exact color of that pixel that you see in a picture that's in actual color. So to represent an image that's in the actually it's not grayscale, it's in color, we'll need 3 channels, and this will indeed be 3D tensor. Any questions about that? All right, so now we are going to denote our image patch to also be a 3D tensor, but now the resolution of the patch is different than the resolution of the image, namely the height and the width of the patch differ. You've seen before we had the full image, and then we broke it down into 9 patches. Each patch was smaller, so HP and WP are smaller than the original H and W, right? It's in the previous, in some of the examples, maybe if I go back here, no. I'm trying to think what are the common numbers. Okay, I don't want to make something up, but you will see, I believe in literature, that these will be 14 by 14 by 3 tensors. Okay, so now, what we are going to do is basically move that window of certain size and take the patches out of the image, right? Such as here. So when I say, moving the window, that means taking this little square and just moving it horizontally. Then when you hit the end, you move to the next possible row, and so on. And you will end up from a whole image with a sequence of these patches P. Now, next step is to do that flattening of each one of the little patches of the image. And we are going to do that by going through all the pixels of the patch row by row. So for example, if you had a patch of the shape 2 by 2 by 3, like here, then we would flatten it into a vector by taking the rows and then again rows. So I hope this visualization makes sense. We just went pixel back value by value, row-wise, and recorded it into a new vector. So this is how we go from this 3D tensor into a single vector for a single image patch. Great. So now we are getting closer to having what is input embedding, right? You might ask, well, Anna, why don't we directly use this flattened vector here as our embedding? And the issue with that is that, as I mentioned before, depending on your resolution of your image, if you have really high resolution, then this will become gigantic vector. And that will cause the issues down the line, because that means that our entire transformer model will be having lots of parameters. So we want to scale it down a little bit, and that's what we are going to do by our favorite technique, which is a linear transformation. So here, our flattened image patch is of the size HP.WP.C. Notice how here we do not have those x's, which means that this is not a 3D tensor, this is a 1D vector. So don't be confused by that. That's very important to distinguish between high-dimensional tensors and just a vector. So this is just a single vector. And then to downsize it to a vector which is of some size d, which is a hyperparameter we set, we just need to do a linear transformation. Now, can someone tell me what is the shape of this matrix W, just as a test to see whether we are getting better at specifying the shapes of our linear transformation matrix? So the question is, what is the shape of W?
I think it should be D by HP times WP times C.
Yeah, exactly. That's correct. So W exactly as, I'm sorry, again, I didn't see who spoke. W is of the shape D times or by, and then the size of our vector, When you multiply it with a vector of this size, you will get with a vector of the size d, which is our goal. All right, so now, perfect. We have for each one of our image patches a d-dimensional vector, which is so close to where we were before. It's actually we are in the same spot as we were with token embeddings. Elham, you have a question?
Yes. So are we gonna embed position for the each pixel of the patches as well?
Yes, we are. That's going to be our next step. So now we are almost where we were, except that we didn't talk about positional embeddings yet. So now for every image patch, we have kind of retrieved them or extracted them one by one in a sequence. So we are going to introduce positional embeddings for that patch. And this is the same way we have done it for text before. So for position 0, 1, 2, 3, 4, all the way to some big number, we are going to create a special d-dimensional embedding that's going to be learned during pre-training. And we are, as we did before, we are going to sum embedding of a given patch that occurs on position I with the positional embedding for the ith position to get the final embedding for the ith patch. And here you might be surprised that for the entire image, which has actually many locations, as many as there are pixels in it, we have used only a single number, but empirically that has been shown to be sufficient to model the position of the patches. Okay, so now we are exactly in the same situation as we were when we were having token embeddings and when we were dealing with text. And I will use this visualization just to go over everything once again. So we started with an image and we divided this image into a sequence of patches. Each one of these patches here is having a resolution p by p, meaning that each one of them is a square matrix. And we have, as again, those multiple potential channels. Then these are vectorized, and we got here p squared c vector. And from those vectors, through linear transformation, which is happening over here, we are ending with a sequence of embeddings for each one of these patches. But we have this extra step where we need to also provide information about position. So we are adding to each one of these patch embeddings, positional embeddings, depending on where the patch occurred at. Okay, is that clear? You can also notice here that even with Vision Transformer, there is this introduction of that special CLS token. And again, it serves the same purpose as with BERT. Once you are done and there is a final token, where there is a final embedding for each one of these initial embeddings, you can use the embedding of the CLS token to denote to describe the entire image and use it for classification, namely just apply the output layer to this classification token. All right, so that's it about Vision Transformer. I will not go into the subsequent layers because not only that you know them and heard about them, you have implemented them in your third assignment. You are all very proficient in Transformer. And the point here to remember, which is a very, 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 very important thing, is that we have only needed to go from whatever initial representation we have into a sequence of embeddings. And this is going to be theme across many modalities when we are applying Transformer to them. All right. Any question about any of this so far? Okay, sorry guys, I also checked chat. I recommend, if you are interested to learn more about Vision Transformer, to check this tutorial. It's pretty good. It has a very nicely written code that you can kind of go through to even further understand what exactly is done for vision transformer and for training one of these. So I highly recommend it. Ryan, you have a question?
Yes. Can you hear me all right?
Yes, I can.
Okay. My question is, so the whole process with an image seems like it's kind of slow. How would this work in like an online setting and like say like a robot that's implementing some sort of like navigation using a camera where it's getting lots of images really quickly, and how is it able to do that in real time when it has to go through a transformer for each image?
All right, yes, transformer in itself is not the fastest of the architecture when we use it for the inference time, but for the training time, it's pretty fast because it doesn't require us, unlike recurrent neural networks, to do anything, in a sequential manner. I don't know whether I have enough knowledge to answer your question deeply, but these things do work for real world applications. So I don't think they are too slow to, deploy them in the real world settings, as I've seen many examples of them being deployed. But I can't specify why exactly that they aren't as slow as maybe you and I would expect. I know this is not a super detailed answer, but I believe that's as much as I can say on that.
Okay, great. Thanks.
Yeah. Elham?
Yes, if I'm not understanding wrong, we are flattening the image in two levels with two times positional encoding as well. Is it true?
I don't know how positional encodings are related to idea of flattening. So can you explain to me what do you mean by that?
Sure. So first, we divide the image into patches.
Uh-huh.
And I guess they have to have the positional encoding to encode the localities in the image. And then we are flattening each patch again into pixels.
Yeah, I wouldn't say that maybe, I'm not sure. Flattening is in a way technical term, which is reserved very often for flattening tensors, which are of the dimension higher than 1 into vectors. So when I say flattening, I really mean take these, tensors, which for us were 3D tensors of image patches, and then flatten them out into a vector. It seems like you also are referring to going from full image into a sequence of patches as flattening. And yeah, I guess that's also true in a way. It is flattening, but I would just be careful about how we use this term because of these, technical specifications that I just mentioned.
That makes sense. That makes sense. But still, I feel like we're getting from an image to a 1D vector in two levels. And I guess I don't understand why don't we do it directly? Why do we divide the image into patches first and then go through the pixels?
Well, we are doing that. We first produce a sequence of patches, and then for each patch, we flatten it into vector and then linearly transform it to downsize the vector.
Yeah, why don't we, instead of going like making the patches, why don't we divide the image into pixels in the first place? Sorry.
Oh, so you mean for a single pixel to have a vector, or what do you mean?
Yeah.
I think that's too fine-grained, right? Like even when we look at, and this, sorry guys, for some of you who don't know about convolutional neural networks, this is not going to be useful. But when you think about convolutional neural networks that were state-of-the-art prior to vision transformers. We also had the convolution being a 2D convolution, right? And we would go over it. And I believe that's just because a single pixel on its own doesn't give you enough information, right? Like a pixel surrounded by its neighborhood gives you an information. So it's too fine, I believe, yeah.
Thank you.
All right, let's move forward. So far we have seen vision transformer. Again, we take an image, provide a sequence of patches, flatten each patch, linearly project each patch, add positional embedding, put into transformer. Transformer will give new embedding for each one of these original embedding, including for the special CLS token, above which we can apply our feed-forward neural layer, or as another term for it is MLP layer, to make the classification. Now, we have learned previously that pre-training, is really, really helpful. So it just makes sense to bring pre-training into this space as well. And this is exactly what has happened in 2021, when another model equally important as BERT has been released by OpenAI, called CLIP. And the main thing that CLIP achieved is a very simple procedure, but it scaled really, really well. So first, with CLIP, we have data set of images which are paired with their descriptions, which is often called image captioning. So you can imagine you have a large corpus of images together with the descriptions of these images. And what people have been trying already before is just training a model by predicting whether a given caption is describing the image or not. But here, creators of CLIP have found a very nice way to introduce a lot of pairs of captions that are not actual captions of the image, such that the model learns representations that are similar for descriptions and images that are truly related and otherwise are different. So let's go over that. So here we have a set of images, so capital N number of images, and we also have a capital N number of descriptions. And CLIP is going to pair each one of the N texts with each one of the N images. So you have N square pairs. However, only those that come from the original data set where we have N pairs are true pairs. They are an image associated with their description. Otherwise, it's an image paired with a text that doesn't describe it. So for example, here we have first image, and here you have all the pairs of the first image with each one of the N texts. Here you have first text and all the pairs of all the images together with that text. And the creators of this model have arranged the data such that true pairs appear on the diagonal here. Okay, so that's what we know so far. And now the goal is that once we have a representation, a vector representation of text and a vector representation of an image, we want the dot product of those two vectors to be high when those are indeed a true pair, and we want their dot product to be low when they are not a true pair, as we have seen many times before. So a way to think about this is if you look at this row only, you can think about it as classification into N possible classes, where the true label is 1 here, because the first pair is the true pair. In the second row, you can again think about a classification of a pair where the true label is 2 because the second pair is true pair. So if you think about this in this way, you can then think about as if we are doing a cross entropy, as if we are doing classification in each row, and therefore we can use cross entropy loss for each row. And similarly, you can do that as for the columns as well. So here you can think about each one of these pairs being as needing to predict where is the true pair, which is in the first position. So amongst these n classes, the right class is first class. And again, then you can use cross entropy loss on each column. And what CLIP does is basically combines all of these various cross entropy losses. So this is a pseudocode for this whole procedure, which I will go through again. So you have your image encoder, for example, that can be, and very often is, vision transformer today. Text encoder can be something like text transformer. Then you have a mini batch of images and text. Here, N refers to the number of images and text you have. Again, you see this notation HWC, and for L it stands for the length of the text. Okay, so let's see. First step is gonna be to take our images and images which we have, it's a 4D tensor, and transform them into a 2D tensor where we have N, again, standing for N images, but now every image, instead of being a 3D tensor, is a vector of the size di. So basically, turn each one of the images into a single vector. And similarly with text, go from L tokens for each text into a single vector, which is of the dimension dt. And this again can be done. Why this is not specified, what exact equations are happening here, because how vision transformer and text transformer work, and you know that you could have added special CLS token in front of each image or text and take the final representation of a CLS token to represent the entire image or a piece of text. So you know what are the operations that give you these kinds of tensors. All right, so once you have that, note that here the dimension that comes from your image encoder and dimension for your text that comes from your text encoder doesn't necessarily need to match. So what you need to do next is to ensure that these vectors are of the same shape. So here, basically what we are doing here is linear transformation. And I don't know why exactly they are normalizing. That there has to be some reason for that, which I don't recall. The point here is that with these operations, you have transform each image and each text embedding into new embeddings that are in the same that are of the same size, which is denoted as DE. And once you have two vectors that are both of the same size, and you want to measure their similarity, well, then you can do your standard dot product. There is this special temperature parameter which you can ignore for now. All right, so basically with these NP dots, you get these values over here, okay? So basically you have produced a matrix that looks like this with these logits. See, it's a square matrix of size n by n because you have n images and n texts. And now you're doing what I told you you can do, which is basically calculate cross entropy loss or negative log likelihood, however you like to call it, across each row and across each column. And the final loss is just the average of those two losses. And then you train the model, you have which pairs should be together and which aren't. The nice thing by doing this is that you have n positive pairs and n square minus n negative pairs. And from what we have seen with, dense retrieval and skipgram, we know that having a lot of good negative pairs is going to be really good for our algorithm because it's going to learn those subtle differences between vectors, which will make it powerful at distinguishing things that are truly related and those that are not related. Okay, now, how do we use a model that's pre-trained in this fashion? Once it's pre-trained, now when it's pre-trained, the image encoder weights are learned and also text encoder, and they are learned in a manner where we produce these representations of texts and images and use the dot products of those representations. The dot products are going to be high for texts and images that are truly related, and they are going to be very small when these things are not related. So, for example, if you want to do image classification with clip, once clip is trained, which it is, and you would just go to Hugging Face or whatever you use to, download it. How do you make a classification? You take an image, you encode it with your image encoder, you project it to a certain size, and then you take from each one of the possible classes, you are going to turn it into a sentence such as a photo of a and then object, such as a photo of a plane, photo of a car, photo of a dog, photo of a bird. And each one of these produced sentences are going to be encoded with text encoder, and you are going to produce as many texts as, as many vector representations of text as you have class labels. And then because your model is designed to calculate dot products such that they are high when things are truly related, you will calculate dot products between your image representation and each one of the text representations. And whatever dot product is the highest, you will predict that's the label for this given image. Okay, is that clear?
Hi, Professor. I have a question. So for the text encoder and the image encoder, do we both have to have a pre-trained encoder for this part?
Yeah, so let me clarify something. CLIP is a model that has been okay, let me start over. CLIP, this specific model has not been pre-trained, so it started from everything from scratch, and then using a large corpus of images with their descriptions and using the procedure I have described, it was trained in the fashion I have described. So because it is very, clear that you can use it for image classification in this way, you can think about it, this is just an image classification model. But that would be wrong. It's not just an image classification model. First, we didn't pre-train it with image classification. We pre-trained it with predicting which pairs of images and texts are related. That's one thing. And the other thing is that since this model has been introduced, it had, because of this training, it turned out to be really good encoder of images. So people today, when they need to provide vector representations of images, they are going to use CLIP image encoder part, which is pre-trained by CLIP authors. So when, today, all of us, we are not pre-training CLIP in this fashion. We are using CLIP that has been pre-trained for various downstream purposes. Does this make sense?
Yes, thank you.
Thank you. Ganesh?
Yes, so my understanding is that like image encoder as well as text encoder, like they kind of get some sort of an semantic information, like maybe like for a dog image, like a dog text, like how that particular, like how we perceive. So those information I think gets carried to both image and text encoder. So does that like is this the same model that's being used for like text to image generation or image to text generation where like these representations like can be used to treat this as like a language translation task, like how we have seen?
Yeah, so that's a good question. So what if we move from classification to generation? If I may distill your question in that way, this is something I'm going to talk about in today's lecture. We are going to need to change a few things because right now with this procedure, we cannot do text generation. So something like clip is can be combined with something else to do text generation, but on its own, it cannot.
Okay, yeah, thank you.
You got it. Devran?
Oh yeah, I just want to ask, is CLIP an acronym for anything?
Oh, I do think it is. So this training objective I have just described, it's called contrastive pre-training. So let's see, CLIP. Oh, I don't see immediate expansion of the acronym if it is an acronym. So I don't know, maybe it is. Yeah, and everyone will refer to it as clip. So if you say clip to people in the area, they're not gonna know what we are talking about. Okay, Fatima says contrastive language image print training. Thank you, guys. Yeah, so this whole procedure I just described, contrastive part comes from contrasting true pairs from pairs that are not related to each other, and then language image because we have both text and image, and pre-training because they introduced this specifically for the pre-training purposes of vision models. Okay, so we have the original repository for CLIP by OpenAI, and you can do zero-shot prediction. You also have it in the Hugging Face ecosystem, and then researchers also independently trained a larger CLIP model. So although you don't have weights of the clip that has been produced in OpenAI, by now we know that it's a common situation with OpenAI, you do have these open versions if you need them. Okay, so now, I started with there are these examples of vision and language stuff we want to do, and we have learned how to encode images to place them into a vision transformer. That's great. Then we have seen how you can pre-train a vision transformer, and now there is a question, but I have a vision and text. How do I use this, or for which purposes? So first, let's look into classification task when you have both image and text. So this is a task that my co-authors and I have created to test models' understanding of humor in the context of New Yorker cartoons. So here you have an image, which is a cartoon image, and you have some caption that's associated with the image. So that's the input. And we have introduced various tasks, and one of the tasks is if I give you two possible captions for this image, which one is funnier, basically. So here we have, I would kill for some cream cheese, and can you please pass the cow? This one was voted higher by actual people who are voting for New Yorker cartoons, and the model should predict that this one should be predicted with this caption. All right, so how do we use what I have just shown you to do this prediction task? So here I'm reusing the image we have seen just 2 slides ago when I told you how to do inference with a clip. And I just crossed out some portions that are not necessary. So when you have 2 possible descriptions of this cartoon, such as those 2 I have just read, you put each one of them independently through your text encoder. And then from text encoder, you will get vector representation of the first candidate caption and the second candidate caption. And then you put your cartoon image into the image encoder. It gives you vector representation of the image, and then you are going to make dot product. and the second dot product should be higher, and we are training the model to maximize this similarity, right? So this is a very, very simple way to do classification of text and images. Basically, you use your clip model and you pass your text through your text encoder and use your vision encoder to encode the image, and then you measure these dot products. And you can, if you have the open width version of clip, you can fine tune the model if you have label data, or you can just do zero-shot prediction if you are dealing with the closed clip. Okay, is that clear? It's very little has changed. It's so simple once you have, once you know what clip is. Elham?
May I ask why is it called classification? Since I guess they're like the captions for different images are not going to be the same.
It's classification because only one of the caption is a true caption here. The other one is not a true caption. So that's the task.
How many classes will we have in the data set then?
I believe it's just, is it matching or not matching? So it's a binary classification.
I see. Okay, thank you.
Yeah, and I mean, I think these are details that are related to this New York cartoon, data set, which is not the point I want you all to remember. I want you to remember that if you have classification of text and images, you use your clip by encoding text, encoding images, and doing these dot products and predicting the highest, whatever is the pair that had the highest dot product to be the predicted class. So that's what I want you to remember. And if you're starting with classes such as, single word classes like plane or car or whatever, like we have seen before, you should follow what clip authors have suggested, and that's to turn those words into sentences. This is a photo of a plane. This is a photo of a car, because clip has been pre-trained with sentences rather than single words. Okay, this is all great, but, and someone has already mentioned this, what if we have text generation problem? What if you want to, given some image and text, what if you want to generate an utterance? Remember the video I have shown you where one of the researchers asked to write a description that she can share on Craigslist, then the model had actually generated the full description. This is not something Clip can do for you. So this is an important distinction to remember. Do you have a classification task, or you have text generation from images and text? If you have generation task, you cannot use Clip because it doesn't have the decoder component. So yeah, this is just another example I want to show you of generation. So here the question is, what is funny about this image? Describe it panel by panel. And then GPT-4 describes what is funny with this image. Again, text generation problem. And here I want to go back to, what we know about language models. We know that we have pre-trained them, then we have instruction fine-tuning and alignment. And this instruction fine-tuning phase is going to be important for text generation from images and text. All right, so for doing text generation from images and text, you are going to have 4 components. You're going to have an image encoder. So you are going to turn an image into sequence of patches, and then you are likely today, almost all papers are going to use a pre-trained vision transformer image encoder that will map each one of these image patches into input embedding and then transform them using many self-attention and feed-forward or MLP layers. So again, here you can use Clip, but just to get the representation of your image. And this is what I mentioned before. You might not use Clip to do the end task, but you might use its encoder portion to just get a representation of the image you can plug into some other model, which will be the thing we are going to do here. So let's say we have our image and we have representation of this image coming from clip and its final layers of its image encoder. Then what is common to do is to take those image embeddings and prepend them to before your token embeddings. Token embeddings that you're going to place into some decoder language model, because decoder language models can decode text for us. And the only issue with that is that, okay, your vectors, your embeddings for your image that come from an image encoder, and those that are, token embeddings for text that are from some other decoder-only pre-trained LM might be of different sizes, or how do you connect them together? So this will be a task for cross-model connector. Okay, this is just a high-level overview of the components. So we will have image encoder, we're going to have decoder, pre-trained LM, and we are going to have some cross-model connector. And now we're going to see an example of that to just make it clearer. So this is a Lava. Lava is a visual instruction tuning, comes from the visual instruction tuning paper. And what Lava does is really actually simple. So here you just have your language model. That can be whatever you like, Qwen, Llama, whatever decoder-only model you have, or a model that can generate text. So here, up to here is what you know so far very, very well. And the question is how to bring into this model, your pre-trained LM, this information about the images. And again, here in Lava, you are going to take some vision encoder, for example, clip. And from image encoder portion of clip, you are going to get final embeddings for each one of the patches. That's going to represent your image. And you are going to, you want to prepend those embeddings before your token embeddings, and then just use your decoder only LM, more or less the same as you have used it before. The challenge is that, as I mentioned, is these embeddings coming from vision encoder can be of size that is different from embeddings that are produced by decoder-only LM you're going to use. So you need to use a projection of your image embeddings into vectors that are of the same size as the token embeddings coming from your language model, which you again do by introducing a weight matrix that you multiply with each one of the image embeddings. Okay, so far so good, except that this newly introduced matrix is not trained yet. It's randomly initialized. So you need to train a model such that this matrix becomes good at projecting these vectors into the right space. And to do that, for example, in Lava, they use vision encoder by using clip vision transformer portion. They use as a decoder-only pre-trained language model Llama. They are using linear projection of image embeddings, initially random. And then they are training their model to follow instructions. And in this way, they are changing what numbers appear in this linear transformation. And in this way, this whole model becomes a good vision and language model. So here, details are a little bit, maybe we'll get over our heads. So I will just mention that creating a great instruction data set for vision and language is harder than just for language stuff, because there is just way less resources that are already out there. So these authors have used GPT-4 to generate some of this instruction data by basically giving some image captioning data and prompting it to generate instruction, as well as some output for that pair. So it's synthetically created data for instruction fine-tuning of this model. Okay, so this bit is not so important for me to understand, for that you fully get what's happening, like how do we create this synthetic data, but it's super important that you understand how can you plug and play clip image encoder with decoder only pre-trained transformer model to do following instructions from both images and text in the input. So are there any questions around that? Ganesh, yes, please, go ahead.
So is there any reasoning for why we prepend these image embeddings? Like, why don't we do like post language instruction or anything?
Yeah, that's a good question. You will always see them coming first. I don't know whether I have very, theoretical reason for that. Maybe someone have tried and observed that it works better when they are prepended. For me, maybe it's intuitive, like you see image first, and then whatever you are telling people next, it's usually in the context of that image. So imagine if you are asking people to do some of these tasks, not models, but people, you would also likely first show the image and then ask, right? You wouldn't just ask and then show the image. So maybe it comes from that intuition, but I don't know. Another reason could be that you want your model to generate text. So these embeddings coming from the decoder only LM are really close to what decoder has seen previously. So maybe there is less disruption if these come first here. Like what is happening here is way more in distribution to the decoder, or to the production of text. So these are some hypotheses. Again, if you would ask me the exact citations for this, I wouldn't be able to give you at this moment.
Okay, thank you.
All right, so I hope that's clear. I think this is pretty simple. You take your Llama, Qwen, Mistral, whatever decoder only pre-trained transformer for text generation, and you just prepend these embeddings coming from your vision transformer that is pre-trained, so likely clip. And you just prepare them such that they are of the same size as token embeddings for the language model. This space has grown pretty substantially recently. So there are more and more vision and language LLMs coming out. This is coming from Molmo papers, whose video we have used to start the lecture. And you can see that these models, that the way they have kind of categorize these models are whether they are API or open weights. And under open weights and data, you will see various models coming up. But also under API models, you see both GPT and Gemini and Claude. So almost all language models that are produced by big corporations today are going to be multimodal, and they will be able to process both vision and text. So this is something I want to draw your attention to. And I just want to go over what, since we started with Malmo, and it's one of the most powerful open weights vision and language models, even more powerful than GPT-4. I want to kind of point to what kind of components they are using. So they have as their image encoder, again, vision transformer clip model. So what we have just learned about. And here, this is referring to resolution. This clip model is trained for high resolution images. So although there is that open weight version, the open weight version wasn't trained for high resolution images. So it's still in some, for some reasons, could be better to get the this clip model. All right, then we have a language model. They have used Olmo, which is produced by the same company, but actually better language model to plug and play is Qwen 72 billion. If you plug this language model with the CLIP model, you get a pretty strong vision and language model. And Malmo is following the same way to combine vision and language by projecting vision embeddings into the vectors of the same size of token embeddings and prepending them to the beginning of the sequence. One thing I also want to draw attention regarding Malmo is that they have introduced a bunch of new useful data sets for both pre-training and instruction fine-tuning, which makes it one of the largest instruction fine-tuning data set for this kind of stuff out there. So if you're interested in this space, this is definitely something to check out. Okay, so now we have about 10 minutes left. And there are a few more things I want to mention regarding video processing and speech processing. I'm also not an expert on these topics, so I will give you pretty high levels, introduction to some of these topics, but I just want to go over them for completion. Because they're kind of popping out now. It's kind of very, very strong new research direction to, not just to research, but also engineering for these people who are producing language models to produce LLMs that can process video and speech effectively, because previously those domains were kind of not ignored, but we just didn't have tools that can process those well. So those are harder modalities. So now their time has come. Any questions so far? Okay. So in regards to video processing is here I'm bringing the figure from Llama 3.2. Llama 3.2 is an open weight model that can process images, video, text, and speech. Here I'm bringing up this figure because I kind of want to make a point that processing images and videos is very similar. You can think about video processing as processing all of the images that make up that video, right? Like video is just a sequence of frames. Frames are images, and therefore you can just process these images directly. If we ignore that videos also have audio, which is not, I know when I said it, I realized it's not such a small assumption to make, but one which we do make. Okay, so here you can see how input can be either single image or video images, but then we have image patches that they do not come only from a single image, they come from many images, right? But once you have, imagine you have your video consists only of 5 frames, and those are 5 images, and each image is a sequence of patch, then you can just continue your sequence of patches, right? So very little changes then. It's just that the sequence of patches becomes longer, and that's it, right? In terms of, using methodology we had introduced so far, but then applied to video processing. Besides that, Llama 3.2 also is doing the cross-modal, its cross-modal component is different from Lava and Molmo, where we had this linear projection of vision embeddings, and we prepended those projected embeddings to the beginning of the sequence. Here, instead, you have these vision embeddings coming from your vision encoder. And then there is a cross attention that is attending from token embeddings back to vision embeddings. Similarly, how we did it for encoder decoder stuff is just attention that goes from one type of vectors to another type of vectors. So yeah, that's a difference. Instead of prepending to the beginning, there is a cross attention to combine vectors coming from different modalities in Llama 3.2. Okay, and another thing we know from this visualization is that image or video processing, it's really similar, except that video is a sequence of images stemming from different frames, and therefore a sequence of patches is very longer. Okay, so to make it a little bit more specific, Llama 3.2 has, as an image encoder, vision transformer that's pre-trained from scratch. It's not clip. It takes 224 by 224 resolution for images, and it uses patches of this of the resolution 14 by 14. Once these patches are flattened and then projected to a new size, you will get for each one of these patch embeddings the size of 7066 AT. And as I said, the cross modal connector here will take features, so embeddings for each one of the patch from 4th, 8th, 16th, 24th, and 31st layers, in addition to the final layer features. So instead of just taking the final layer features, their vision cross-modal connector will look into the previous representations as well. And again, instead of prepending these to the beginning and of the decoder-only transformer, they are introducing a new cross-attention where decoder portion will attend to these vision embeddings. And one thing to remember here is this information that they provide, which says that introducing this cross-attention introduces a substantial number of parameters into the model. They say for their largest model, which is of size 405 billion, the cross-attention layers account for a quarter of those parameters, so almost 100 billion parameters, which is a lot. It's a huge number. And for their language model, they are using Llama 3.1. Okay, I'm going to wrap with a sequence of details, nitty-gritty details that you do not need to know. This is maybe for people who are interested in extra advanced stuff in this realm. But I will go through them because I have 3 minutes, so this is perfect time to go through this. So for video processing, Llama 3.2 takes as input 64 uniformly sampled frames from a full video. So we can't process every single frame in a video. That's too many frames because each one of these frames is going to be a sequence of batches. And even when we do this kind of sampling, you will end up with 50,000 of those embeddings that we have introduced from those patches. So it's a lot. So we can't really consider every frame. But once we sample, each frame is going to be processed by our image encoder. And now, we have a sequence of patches, but these patches come from different frames. And there is a question also how to encode a little bit more of temporal information. And how creators of Llama 3.2 do that is to first basically aggregate information from 32 frames into a single frame. And for this, they use something that's called perceiver resampler. This is where things get a little bit, I would say, we are going now into very deep details, but maybe the way to remember what perceiver resampler is, it's a technique to handle time and memory requirements that come from self-attention. Remember, self-attention is introducing quadratic complexity with respect to the number of inputs. So for us now that we are using vision transformer, the input length is determined by number of patches, which can be very, very many if we have lots of frames. So what perceiver resampling is doing is it's introducing these latent arrays, which are the number of those is way smaller than the number of patches you have. And then the self-attention is done on these latent arrays rather than on the input tokens. And in this way, the attention that works, self-attention, which works with those latent arrays, is going to be way cheaper than if we have used the original token embedding. So again, this is way out there, extremely advanced. I don't expect any of you to know, but if this is an exciting area for you, this is an important component of being able to process videos. And Another thing that's done is extra video cross-attention layers that are added before every fourth image cross-attention layers. So it's a lot. It's becoming more complex, right? And video processing is definitely not there yet. You know, I was at EMNLP last week, and I've seen posters that show how these things fail tremendously if we introduce just slightly more distractors. So it's definitely an area where large language models are still not very powerful. So if you are in the beginning of your PhD looking for research directions, I think there is quite interesting stuff to do here. Okay, it's time to 46, so I'll stop here. I will stick around for a little bit more if there are any questions for me. Thank you.